Kinematics of rigid bodies. We're going to go ahead and revisit Chapter 11. Do you guys remember the difference between kinematics and kinetics? So kinematics is just a discussion of the motion without reference to the forces that cause them. So no free body diagrams or anything like that yet. We're just going to be looking at things like constant acceleration problems and v equals dx dt, a equals dv dt, purely, some calculus relationship type things. And then next chapter we'll look at kinematics and start doing the force balances and that kind of stuff. And the only difference between what we're doing now and what we had been doing is we're not looking at particles anymore. We're looking at rotating bodies, so where different pieces of it have different velocities and accelerations. So once again, we're going from just a single particle to moving around to something that the different corners of it have different velocities, and it's just going to be a little bit more complicated than looking at a single particle, but we're going to be using some of those same equations that we had already used in Chapter 11. Okay, so the different types of motion. What's going on with this train here, this would be curvilinear translation, where all the points on the object are traveling at the same velocity and acceleration. This is going to be the simplest kind of motion. We'll have motion like the rotation around a fixed axis. So if you want to know the velocity at each point along this fan blade, what would it be? Here's another rotation about fixed axis with a planetary gear system. Okay, so let's just walk around and consider some of these different types of motion. So we have some potato-ish looking blob of an object, and let's say we know what the velocity of point A on that object is, and we would like to know what the velocity of point B on that object is. This is going to involve some vector analysis and relative velocity calculations, as well as relative acceleration equations. Okay, so if I want to know the velocity of B, that is going to be equal to the velocity of A and the relative velocity between B and A. Or if I want to look at positions, or if I want to do accelerations, it's the same thing. This equation here is describing the vectors that you're seeing here. So the blue vector, RB, is equal to the red vector, RA, plus the relative motion. What this is doing is, if we know the velocity of one point on that object, and then we also know how it is rotating or moving around that one point, then we can get the velocities of any other point on there through just RA plus the relative velocity equals RB. So we're doing these relative motion equations on here. Okay, so that goes from positions and relative positions to velocities and relative velocities. Now, if we're going through regular rectilinear or curvilinear translational motion, if it is not rotating at all, that means their relative motions are zero, which in that case they would have the same velocity. And in the case where their relative motions are the same and the relative accelerations are the same, then all of the points are going. So this is the case where you have everything is moving together and the potato is not rotating. Rotational motion, that's where you get this relative velocities and relative accelerations. But for all of them, it's going to be a vector analysis and draw out these vectors. So it's not just like 3 plus 5 is 8 or something. You have to look at the directions and add them as you would add any kind of vector together for this. Okay, before we hit all of the curvilinear motion and circular motion, motion around a fixed axis or a fixed point, let's just review the Chapter 11 stuff for circular motion. And a lot of the circular motion derives from this kind of stuff. V, remember V is always tangent to the curve, and it looks at the arc length, so how far around this curved line you've gone, how far, it's ds over dt. and the arc length is equal to r d theta dt. If you have a constant radius, then your velocity is r times omega, where omega is your change in angle with change in time. And you can remember this by just remembering what the circumference of a circle is, right? So circumference equals 2 pi, some angle times r, right? Or if you want just half a circle is pi times r. Or some little sliver, any kind of an arc length is going to be the angle in radians times r. And if you simply take the derivative of this with respect to time, that's what turns into velocity. So v equals r d theta dt. And you can remember that from circumference, some kind of an angle times r. So it's how the angle is changing times r for constant radius problems. Okay, so if that's our velocity, there's the arc length, there's our velocity, there's our angular velocity. So just try and remember the definitions for this. So omega, that's almost like two v's smushed together. Omega is talking about how fast the angle is changing with time, versus if you want meters per second instead of radians per second, you have to multiply it by that radius in front of it. Okay, if we take another derivative, we will get one of the pieces of acceleration, the tangential piece. So r, and the second derivative with respect to time of angle, that's our alpha. Alpha, that kind of looks like an A, right? And alpha is just looking at how fast that angle is changing with time. Those dots are just derivatives with respect to t. So r theta dot, that's d theta dt. And if you take the second derivative, that's for acceleration. Okay, so there's our angular acceleration is alpha, and that's the tangential piece. So that's what goes along with the tangential piece of velocity. Okay, there's two pieces for that angular acceleration. We have the tangential piece, which is how fast the magnitude of velocity is changing. And there's also the normal piece of acceleration, which describes how the direction of acceleration is changing. So the particle wants to go flying off in a straight line, and instead of going in a straight line, it's getting pulled back to the center. And that change in direction, that's the v squared over r, or rho if you have something that's non-circular path. So just v squared over r. And that comes from taking the derivative of not just the magnitude of the velocity, but the magnitude of the velocity, and also looking how that direction changes. So here's that derivation again, and you're looking at how fast the magnitude changes, and that's in the tangential direction, and you're looking at how fast the direction is changing. And if you apply a chain rule to this, this is where that v squared over r comes to. So it's a quick substitution. ds dt is velocity, r d theta is ds. This is like circumference equals 2 pi r kind of a deal. And then how that tangential direction is changing with theta, well, that's in the normal direction, right? So instead of shooting off in a straight line, it gets pulled back in the normal direction. And you put that together, v times v, you get v squared. This turns into 1 over r in the normal direction. So there you go. There's the normal and the tangential pieces of your acceleration. So really make sure that you have this in your mind, because we're going to be using it a lot. And now instead of just a single particle, like a tennis ball on a string or something, we're going to be looking at objects that are rotating around a fixed axis, and different points on that object will have different velocities depending on their radius with respect to what they're rotating around. Okay, so here we go. Here's our potato. Our potato is on a shish kebab stick, and we're rotating it around the fire. And we want to know the velocity of some point P on this guy. So what we're going to do is we're going to have to figure out how far that point is from our axis of rotation. And maybe we have some position vector with respect to the origin, and we have some angle. So then what would this radius be? Well, SOHCAHTOA, r sine theta, that would be the opposite side of that little triangle. This is a right triangle coming off of here. So just look at the diagrams, look at the pictures, and figure out what that radius is, okay? So here we have the position vector, our sine theta. That'll get the distance from the axis of rotation to where the point is that we're interested in. And if this guy is going in a circle, that circle is just a little two-dimensional slice. So you're looking for those two-dimensional slices in your three-dimensional object. And then for each of those slices, velocity equals the arc length, change in arc length over change in time, which is, if we look at r sine theta, d theta dt, okay, so r omega, and then we have to make sure that we're catching that distance from the axis of rotation to whatever little particle we're interested in. So it's looking like it looked like before. Okay, here we have v equals omega cross r. So this is the new piece of it. Remember what cross products do. Cross products find the perpendicular distance between two vectors. So we have the vector omega. The blue vector is omega. So when you're talking about the vector for rotational motion, it's describing the axis of rotation. So you can't really draw a circle for a vector, right? So if you take the cross product between omega, which is pointing up, this blue vector, and our position vector r, okay, that's going to give you your velocity. And just look back through your notes for how to calculate moments to see the position vectors for things. So you're going to split omega into ijk components, your position vector into ijk components. You take the cross product of these two, and that will get you the velocity of the particle. So just remember how to do those cross products, and you will be set. Here we go, concept quiz. What is the direction of the velocity of point A on the turbine blade? Okay, so we are rotating counterclockwise, which would, using the right-hand rule, we are unscrewing this thing. It's coming out of the board at us, so that would be a positive rotation. So the omega vector is sticking out of the board towards us. Okay, so in this case, A would be going straight down. Okay, so there's straight down. What would this look like in terms of a cross product though? Okay, so omega cross r. In ijk components, if x is to the right and y is up, what is omega's ijk components? Remember, this vector describes the axis it's rotating around. So in this case, omega is rotating around the k direction, and our radius is from the axis of rotation to the point that we're interested in the velocity. So we're going into the left direction, so that would be negative I. Negative Li would be what our radius is, and if you chug through the cross product on that thing, you would get our velocity would be in the j direction. So k cross I gives you a j direction velocity. Here's the cross product written out. So we have, here's I is 0. Here's j. Remember, j goes the opposite direction, so omega cross L, and it ends up being negative. And then here's k ends up being 0 too. So for these guys, it's a cross product, just like your old moment calculations, where you're going to put the ijk components of your rotation in the first row and your position vector that goes from the axis of rotation to the point where you're interested in that velocity, and chug through that cross product, and that will get you the magnitude and the direction of your velocity. Moving on to acceleration. So acceleration is change in velocity over change in time. Velocity, we just learned, was a cross product, omega cross r, how fast the angle is changing times how that position vector is changing. Okay, if we split this apart, so omega dt cross r, omega dr dt, what this turns into, the omega dt, that is the change in magnitude. This is your alpha cross r. This is the tangential piece of your acceleration. And it looks kind of like it did before, but instead of just our alpha, we have a cross product now. And then omega cross v, v is equal to omega cross r, so we end up with two cross products, and this is the normal piece. So v squared over r, or r omega squared, only now it's not just r omega squared, we're using the cross products, and this will get us the magnitude and the directions of the accelerations, and you'll have to add together the tangential piece of it and the normal piece of it, and these are vectors that you're adding together. Okay, so here is the angular acceleration. That's how fast omega is changing with respect to time. So in a 2D slice, all of these angular accelerations and angular velocities, they will be coming out of the board at you around that k-axis. Okay, so those omegas and alphas, it describes the axis it's rotating around. So we're rotating around the k-axis if you have this 2D slice happening here. And just remember the order of these cross products. So alpha is first, cross r, and then omega cross r. If you want to split this up and just figure out what the velocity is, and then just do the cross product with the velocity, and usually if you figure out what the acceleration is, you've already been figuring out what the velocity is anyway, so you can just plug your velocity in here. And the total acceleration, it's an a squared plus b squared equals c squared kind of a deal. So you're adding vectors together. So it's this normal direction, r omega squared, or omega cross r, and then you have your tangential piece of it, alpha cross r. And these guys are perpendicular to one another, so to get the overall acceleration, yeah, just a squared plus b squared equals c squared. And you'll have to kind of look at those vectors, draw them out so you can figure out what the angle is for them. Okay, so let's look down at a slice of that potato where here's the axis of rotation is our origin, so we're going from the axis of rotation to where that particle is. The velocity is omega cross r. Sometimes it helps to kind of draw in the path of each of those particles. Rotational motion, so here's the velocity, omega cross r, and here is the acceleration. The normal piece of acceleration always points towards the axis of rotation. Tangential could be speeding up, could be slowing down, it could be going left or right. So you don't really know the direction of tangential, but this normal component does always point towards the axis of rotation. It's always pulling it away from that straight line motion and keeping it going in a circle. Okay, let's go through a couple of examples here, and then maybe this stuff will make a little bit more sense. Okay, what is the direction of the normal acceleration of point A on the turbine blade? We're not looking for the entire acceleration here, we're just looking for the normal piece of it. Okay, so remember which one the normal piece is? Here what we have is this guy, okay? That's the normal piece, omega cross r. Omega cross r. Remember the omega cross r piece of it, that's your velocity. And we already got our velocity, so let's just do a cross product with our velocity, because then that's just one cross product to do. Okay, so here's what we had for our velocity. So omega cross r, you end up with omega L, negative omega L in the j direction. One more step, so omega cross v, so here's our omega, here's our velocity, and that is going to give us, remember it's 0 times 0 minus omega cross negative, so it ends up being positive. So positive L omega I. If we drew that in here, we would be going in the positive I direction. So that would be our normal. And remember, the normal acceleration, the normal piece of it, always points towards the axis of rotation. So which one is that, A, B, C, or D? That would be A. So we're just going straight in the normal direction over here. Okay, next up, what is the direction of the tangential piece of acceleration? So now we're going to look at alpha r. This is the change in the magnitude of the velocity, the tangential piece. Let's walk through this cross product. Okay, so alpha cross r, you're going to put alpha on the top. Remember, alpha, the direction of this describes the axis of rotation. And they say the angular velocity is increasing. So that would be coming around here in the counterclockwise direction in the positive k direction. So we would put this over here in the positive k direction, and then our position vector is from the axis of rotation to the point we're interested in. So in this case, we're traveling to the left, and we're looking at a negative L or negative R in the left direction. That's our position vector. So alpha cross R, and this is going to give us something in the J direction. So J, we go from the right to the left, and we have to keep that negative sign on there. So here's the direction of the tangential acceleration. It is in the negative J direction, and that makes sense, right? That the velocity is increasing, so that means that tangential piece of it is down. So we have the tangential piece down and the normal piece towards the center. Okay, so now that we know the normal piece is towards the center and the tangential piece is down, if we add both of those vectors together, what direction is it going to be in? So add them head to tail, and here we have something pointing down and to the right for our overall acceleration. So hopefully that makes sense. That was a pretty simple example, but if you can just see how those cross products work out, you're going to break everything into IJK components and then just chug through those cross products, and it's not too big of a deal.